Okay, just to also let you guys know that I'll be recording the lecture, okay, just for revision purpose, okay, but I won't put out straight away after the class. Usually during the midterm review, and I'll put out some of this past lecture, okay. So let's get settled down. Okay, so this is ECE 486, Modern Control Theory for the graduate student. It's ECE 486 for the undergraduate student, okay? Later on, I will give you more information about the course syllabus and content. All right? Okay, let's get started, okay? Yeah, there are plenty of space in front if you um, want to occupy them, okay? If you can't see the screen. Any point of time, if you can't hear me, just feel free to interrupt, okay? Let me know, right? Okay, so in this class, we're going to have a graduate student as well. It's actually undergraduate student doing ECE 486 control system. There will be graduate student also taking the lecture as well, but they will not be doing the exam or lab. Okay, they will only be doing a special project. Okay, so a bit about the course description. Okay, so at the meantime, please take a look at the materials on Blackboard as well, okay? If you have access to Blackboard. If you haven't and you're enrolled in this class, please let me know, okay? Especially some of you who just registered, all right? I will include your name in Blackboard so that you can get all the materials. But basically in this course, we're going to look at the design of control system. Okay, it's more of helping you to understand how some of these control theories can be used to analyze and design. Okay, so the first part is roughly about understanding the dynamic system, okay, being able to describe, represent, or model this dynamic system. And then after that, you can actually start to do some analysis, especially stability analysis, and later on using what you have learned to try to design control system. Okay, so strictly speaking, there's three parts, not just analysis and design. There's also modeling. Okay, the first part, or rather the first 3 weeks, will mainly be covering the topics on modeling, right? Okay, so like the second bullet point is saying, is actually emphasizing on modeling state variable representation. Okay, so once you are able to represent them in standard mathematical way, okay, you can start to use computer to analyze them and also help you design some of the solution. Okay, so for the undergraduate student, okay, you will be doing lab. Okay, this course is going to be quite intensive in terms of the lab. Okay, you will have 7 lab session. Later we go into detail, but the lab is to help you relate what you learn in theory better with hands-on experience. Of course, graduate student, you are welcome to come and take a look, okay, even though it's not compulsory for you. Okay, so you will be covering the following topic, okay, mainly modeling of this dynamic system, and of course the dynamic response. Basically, how the system will behave, okay? Try using. Yeah, I think it's harder to use this. It's not loud. Uh, Let me try using the mic. So sometimes when I write, I will just put down the mic, okay? So it will be a bit taking a little bit. Okay, basically, dynamic response is talking about how, or it's about how the system will behave, okay, in a dynamic sense. And then after that, you will learn a few tools, okay, that will help you analyze this control system that you design. Okay, so root locus design method, okay, frequency response design method, and finally state space design method. Okay, maybe now all this will not sound familiar to you. Okay, might be something new, but it will be clear as we move on in this course. Right. So yeah. So the learning objective here, okay, to acquire this design-oriented approach, okay, so that you will develop this ability to kind of build your control system, but it's more also for a prerequisite to later more advanced courses. Okay, so in this control system course, is going to cover classical control and a bit of the modern control. Okay, uh, actually about 30% of this modern control dealing with state space, stuff like that. Okay, so when you go on to more advanced topic, you will actually get more in-depth information about this. But of course, for the graduate student, okay, you will be doing projects that will give you more perspective on modern control. Okay, and so in this course, the other objective is to uh, familiarize you with some of this basic concept, okay, and then master some of this design methodology. Okay, so later on after the course, you should be able to like know how to select certain parameters, okay, certain variables so that you will have a stable system and a system that will fulfill your uh, so-called uh, specification. Okay, later on there's a this dynamic response, okay, where you will need to be able to uh, specify the system dynamic response. Okay? Okay, so before we really go into detail, okay, just a very quick self introduction about myself. Okay, so the courses that I'm teaching. Okay, some of you probably have taken my course previously. Okay, but mainly I do most of the control dynamics as well as signal processing course and also robotics, which is my main background. Okay, so this semester I'm doing control system, okay, which is this class. And usually in spring semester, I will do introduction to robotics. Okay, some of you have taken this course as well. Okay, for research, I'm a robotics person, so I basically work on robotics. So these are some of the areas. Okay, we do not just the um, mechanism of the robot, also including the perception. Okay, how the robot understand the surrounding and be able to react to the surrounding, and control of the robot, how we achieve what we want the robot to do. Okay. So it's quite self-explanatory. Okay, my research background. Most of you will know what is robotics, what is control, and what is perception. Right. So in this course, some of the administrative methods that uh, can take note of, but I think these are all documented on Blackboard. Okay. Actually, mainly for the undergraduate students. So you should have prerequisite. Okay. The idea here is to be able to feel comfortable working with complex number, linear algebra. Okay, linear algebra is actually a class, right? Uh, but you should be able to work with complex numbers, all right? And so this is the reference textbook that we're going to use, okay? But it's actually not compulsory. Okay, the lecture notes should be self-contained. Okay, most of the time you should get what you need in the lecture notes, but it is a very helpful textbook, okay? Some of the practice problem are also very useful. Okay, consultation. Um, Once we finalize the lab grouping, we will fix a consultation date. Okay, usually I will put it in one of two of the lab section. Okay, but let's wait for the finalization of this thing. Okay, so grading policy. This we will actually formally announce it again. Okay, this doesn't apply to graduate student. Okay, you will be doing slightly different this grading policy. But for the undergraduate, okay, you will have your class participation, 5%, homework 20, lab 30, midterm 20, and final exam 25. Okay, so this is actually the same as UIUC uh, configuration for the grading, right? So more on the admin matter. Okay, the main difference here for the undergraduate student, you're going to do a lot of lab. Okay, actually not a lot compared to other class like robotics, but it's pretty substantial. Okay, you will have, um, to be exact, it's actually 7 lab, but the first lab, lab 0, is just a familiarization. So we are going to start next week, okay, week 2 for lab 0, okay? So it should be quite straightforward. I think all the materials are already up, okay, right? Including all the codes. So you can take a look at this, okay, to get yourself familiarized, okay? Then there will be a National Day holiday in week 3, and then week 4, we will start lab 1. And so it's always on the run week, okay, week 4, week 6, week 10, 12, okay? So that will be the plan for lab session. Okay, we will talk more about this during your labs. Yeah, we are also trying to organize it in a more optimal way. Okay, because right now there are only like 4 or 5 in some of the group. Okay, so for those who are in Wednesday lab group or Friday afternoon, try to take other lab groups. Okay, because there are only like 4 or 5 of you. Okay, we will try to group you uh, together with the rest. Okay, so that it's like optimizing the resources. Right. So we will see how it goes. Okay, so for those who are in Wednesday lab group or Friday afternoon, try to see if you can squeeze into other lab groups. Okay, other than these 2. Okay, this is for the undergraduates. Okay, if not, we will come out with a finalization next week when you are there at the lab zero. Okay, so for the graduate student, okay, this is your part. Okay, all the graduate student, you will be doing a special project, right? So in this project, you're going to you will have 4 options. Actually, the last option is something new. Okay, we tried out in the other course for robotics. It turned out to be quite okay. Some of them actually choose it. So you can consider that. Okay, so basically educational walkthrough. Okay, you can either give a demo or a tutorial video, and then after that do a presentation. So this is also kind of related to undergraduate student because at the end of the semester, there will be a mini symposium, okay, where the graduate student will be uh, doing a symposium presenting to the rest. Okay, so in the past, we only do it within the graduate student, but now we are trying to extend invitation also to undergraduate students so that you can join. Okay, we did it for this last year actually. And then of course, some of them get a bonus point for undergraduate participation. Okay, you will do some feedback to evaluate the graduate student work or their presentation. Okay, so it's actually quite fun. You get to learn new stuff. You get to also experience this kind of academic activities and also to get bonus points. Okay, trust me, at the end of the semester, you will probably want to get some bonus point. Okay. Okay. So that is the part on the administrative stuff. Okay. Of course, for the graduate student, more information about your project will be up in Blackboard, and we will actually discuss on site as well. So this is our teaching team. So as most of you know, this is actually a, course that is also taught by UIUC professor, or in this semester, uh, um, Professor Bilabas, okay, Professor Muhammad Ali Bilabas will be doing. So in fact, he will start his lecture next week, but because of this timing, the time difference is a little bit challenging for him to do real time or live lecture. So it might, it will actually be a recorded one. Maybe Thursday he will be doing a live lecture because Thursday is, sorry, Tuesday. Tuesday might be a live lecture because it's more manageable, okay? Uh, but I will update this formally uh, before next week, okay? So if not, it will be a recorded lecture, okay, if the timing is too challenging. But current plan is that Tuesday will be online live lecture by Professor De La Paz, okay? Okay, so he will be doing the um, week 2 materials. Actually, week 2 and week 3. We will finalize this done in our same plan. Okay, and yeah, of course, myself, I'm also doing this lecture too. So we are also quite fortunate to have a group of dedicated teaching assistant, right? 4 of them, okay? 2 of them PhD student and 2 of them master student. Okay, yeah, for the undergraduate student, yeah, please interact with them during uh, this lab as well, okay? Especially if you want to know a little bit about graduate life. And of course, your fellow classmate, graduate student course. Okay, the good thing about this is that you get to interact with graduate student, okay? Whether it's a TA or a classmate, all right? So for the graduate student doing special project, of course, you can look at their expertise because the some parts, of course, subject to availability of resources. Okay, you can actually propose some project that do something physical. I'm not physical, or something that will have a physical setup. All right. Okay, so you have 4 of them. All right. Okay, so that is very much on the administrative part of this course. Okay, uh, today we will start on a very gentle introduction on feedback control. Okay, so it's more of a conceptual overview. Okay, answering what is feedback control, why do we need feedback control, and a little bit on how we implement it, okay? The general architecture. So today's lecture will be uh, slightly more gentle, okay, not as intense. Okay, so any point of time, if you have questions, just feel free to raise your hand and ask, okay? You don't have to be shy, all right? So it's afternoon, that's why the energy level might be a bit low, including for myself. Let's try to make this lively, okay? So after this lecture, okay, we should be able to understand the concept of control system, okay? So this lecture is going to give you the introduction, okay? We understand what is feedback control, and then be able to appreciate uh, this feedback control system as a mean of achieving something more reliable, okay? If you are trying to design something, a solution, okay, um, later on, you will see that there are many ways, okay, but using feedback control, you can dynamically uh, alter the system or change the system to the behavior that you want. Okay, that's why we want feedback control. So later on, at the end of the lecture, we also take a very brief look at the past, present, and prospective development in this field of control. All right. Okay, so I'm sure most of you heard of what is control system. Some of you also have some background in this area. Okay, uh, let's uh, let's come to a common definition in this context, or at least for this course. Okay, so this control system in this course, we're going to find it as a design, this design system, okay, that is going to achieve certain desirable outcome or targeted output, okay, by generating the appropriate input. Okay, so we are usually dealing with a dynamical system, right? And most of the time, we want it to be doing something within this specification performance criteria. Okay, that means we set certain criteria that we want the system to be able to do. So a very quick illustration. Okay, so let's say you have a system represented by this box here. Okay, so this system will actually behave in certain way. Okay, it may have an output if you give a certain input. Okay, so it may have a certain output, even certain input. Okay, but as an engineer, maybe you can design this system. Okay, you can choose the right material, right component, so that the input and the output, or rather the output, the input will map to the right output that you want. Okay, you want the thing to be resistant to disturbance and things like that. You can design something with high damping coefficient. Okay, to kind of attenuate some of the external disturbance. Okay, and you can design that. But once you design the thing, you probably cannot change the parameters. Okay, so as a control engineer, okay, you can actually design something that we call controller. Okay, so you can design one more block called controller, and this controller can actually tell you what kind of control input to send into the system. Okay, so that the output is what you want. In control terminology, we call this a reference. Okay, you can actually send in what we call reference. Okay, so that this controller will come out with a control input that will send into the system and produce the right output that we want. Because later on, you will know that this, in control terminology, we call it plant. Okay, the plant that we're interested in controlling. But this is just a very broad overview, a conceptual overview. Okay, so most of the time, this system is not static, it is dynamic. Okay, that means it will change over time. Okay, if it's static, you can just work out a certain equation that can just give you a mapping between input and output. You don't really need a controller, or rather, your controller could be just the inverse of this equation. Okay, we will come to this later on. Okay. So that is roughly the concept of control when we are in a certain environment, dynamic environment. We want something to happen. Okay, we can design a controller that can help us achieve that. So we can take a look at some of the example. Okay, just by looking at the definition, it might not be very helpful. But if you can relate to some of these example, okay, it will actually give you a very good sense of what we are talking about when we look at control system. Okay, so one of the most commonly used example, or especially historically representative of control system, is this centrifugal governor. Okay, so in a way, this kind of control the airflow, okay, into this steam engine. Okay, so it's one of the representative invention during the Industrial Revolution. Okay, when they start to need to put in steam, this steam engine. Just to make sure that this is correct. So what happened here is that you want to control the air flowing into the inlet. Okay, so this arrow is kind of like the air trying to go into the inlet. And you want to control this automatically, or you want to regulate this. Okay, so one method is to build this centrifugal governor. Okay, so as this air flow in, okay, this will actually spin. Okay, and this spin, because of the centrifugal uh, effect or the centrifugal force, it will actually leave the ball, okay, going outward. Okay, so when this ball is lifted outward, okay, it's going to uh, trigger the lever. Okay, so there's actually a lever here. Okay, and when the lever is triggered, the opening will actually be changed. Okay, so this will regulate how fast the air is, or the gas is going to flow. Okay, so this is kind of self-regulating. Okay, you build something like this to control the airflow. So it's a very good example of control system. Okay, of course there are many simple and elegant control system like this. Okay, your flushing system in the toilet. Okay, how to control the level of the tank in the behind the toilet bowl. Okay, so that you get the right amount of water using a floating device. Okay, so all these are control systems. It doesn't have to be electronics, or it could be simple mechanical design. Okay, but of course, a lot of time we can tap onto some of this uh, electronics or this technology involving electronics, like having this active suspension. Okay, so this active suspension system uh, is actually to help cancel out some of the disturbance when the car is traveling on the road. Okay, so let's say this car is traveling on a bumpy road. Okay, there will be sometimes there will be uneven terrain. Okay, there will be a bump on the ground. Okay, and you want the passenger or the driver to feel comfortable. So you can put in spring and damper. Okay, if you are a mechanical engineer, you can design the right spring damper so that it will kind of have this suspension effect. But when you do that, you kind of already selected all your um, this component. You can't change it as you are driving. Right? Not change it halfway. So one way is to use active suspension. Okay, the word here active in a way is dynamical. Okay, that means you are actually using feedback control. You are actually using some ability to sense external situation and then send out some signal that will cancel out. Okay, so this part here, okay, it is actively canceling out uh, this um, bumpiness of the car. Okay, so later on we will see that feedback control is something that can help us achieve what we want in a dynamical system. Okay, of course, you know you can put in very this buffer or dashboard for damping effect. But once you do that, you can't change it dynamically. Okay, so active suspension system is slightly different. You actually use this feedback to help you cancel out what you don't want. Okay, so it requires you to build this feedback control system. Okay? And of course, air conditioning system is another very common example, right? Because let's say in a room, you want it to be at the right temperature, and sometimes the people go in and out will change the whole environment, okay? So the more people you have, maybe the room get very hot, okay? And you want to control this temperature, okay? By using thermal sensor, okay, to sense the temperature and then give the right input to this whole system, okay, either by increasing the temperature or lowering the temperature so that the temperature will be just right. Right? So this is one good example. Okay, and motor control, you also use this to control your motor. Okay, sometimes you want the motor to be moving at the right speed, okay, or to the right position. Okay, you can use control method to dynamically achieve this. Okay, so when there's a loading involved. Okay, sometimes you will need to overcome some friction, overcome some in this inertia of the load and everything. Okay, it is important to have this sensor to sense uh, the current speed and then make the right decision or uh, right control input, as we call it in control terminology, to make sure that the speed is at the point that we want. So active noise cancellation is kind of the same as this active suspension. In a way, let's say if you are in a noisy environment and you want to get rid of the noise, the surrounding noise, okay? Of course, one good way is just to use very thick material, cover it, okay? So that all the noise get attenuated, okay? That's one good way. But sometimes you still want it to also, you still want to have some ability to hear what is happening in the surrounding. Okay, so once you build something too thick, you can't hear that. Okay, it's true that you can cancel the noise, but you also uh, lose your ability to hear understand. Okay, so if you use this active noise cancellation, okay, it's actually dynamically sending out a signal that will cancel out this noise. So of course, active noise cancellation, maybe it doesn't perform, it is quite challenging when you're dealing with high frequency noise, right? Okay, so you know that in a case like that, you kind of need to have good high control loop, the um, loop of your controller that you design it to be uh, high, right? But for this choosing the right material, maybe you choose something very thick. Okay, it can actually be quite robust against high frequency noise because they will just attenuate it. But maybe for low frequency noise, it's not so good. Okay, not as powerful. So sometimes you do a combination of this. Okay, you also choose the right material and also choose the right or design the right control system. Okay, so this is uh, another example. Okay, but the gist here is that you are also taking in the information about the surrounding and then using this information, come out with something and input to the system so that the system will behave the way you want it. Okay, so in this control system, we're going to learn how to design this block here that will help us come out with the right control input. Okay, and there are more sophisticated stuff like the heart lung machine, because we see things like mechanical, thermal, electrical, electromechanical. Okay, we see a lot of this example. But if you look at this heart lung machine, it's something very sophisticated and include all domain, okay, including this chemical exchange of gas, temperature regulation, stuff like that. Okay, so this is one example. So we know that in our body, we have our heart and lung to help make sure that we operate or we stay alive properly, right? The heart kind of send all the blood with the right nutrients, oxygens, or the stuff that you need to different part of the body at the right level. And your lung kind of take in air, oxygen, okay, uh, send it to the blood and the blood send it to the body. Okay, so this is important. Even biologically, this is a control system, but maybe not artificially designed by you. So what happens is in surgery, sometimes you might have to stop the heart, okay, in order to operate on it. So uh, the challenge here or the solution required here is to have something that will replace your this heart and lung during the surgery. Okay, so in a way, it is like the idea that we talked about earlier on. Okay, you have a system and you want it to still operate or function properly. Okay, you need to design something that will take over the system while it is not doing the job. Okay, so in a way, you are designing something artificial to make sure that it works like the heart. So there will be something that works like the heart externally and something that works like the lung, okay, to do all the uh, transfusion of different chemical uh, stuff and the sending or transportation of the blood to different part of the body. Of course, in between, you need temperature regulation to make sure the temperature is correct, the concentration level is correct, etc. Okay, so this is something very sophisticated. So this is, of course, a real this transportation system of your, we call that this cardiopulmonary, okay, your heart and lung. And of course, we can replace it with something artificial. See if I see. Okay, so this is a sophisticated control system. So a lot of time when we talk about control system, we think about mechanical or electrical stuff, but it can actually, or sometimes at most thermal, flow rate, etc. But in engineering example like this, you see how sophisticated it can be. Okay, need to design something that replace the biological system of the human body. Okay, so this is something very interesting. Okay, once you are able to so this. Yeah, so basically once you're able to get this out, okay, you are actually able to regulate this um, blood flow and exchange of oxygen level, etc. So we kind of answer the question of what is control system, or at least look at this question on what is control system. We look at a few examples. Okay. The next thing is to ask why do we actually need control system or actually feedback control in this context. Okay. A lot of time we are looking at having the system to be able to sense the surrounding and use that information to come up with the right control input so as to send it to send the right control input and achieve the right output. Right? So there's a control problem. Okay? So in asking ourselves why do we need that? Okay, there are a few reasons for control system. Okay, power amplification. Right? We want to maybe send in a not very heavy duty input, but result in a very large output. Okay, it's like power amplification. Okay, so in the case, let's say if we want to carry something very heavy, so let's say in this case, you want to carry something very heavy. Okay, one way is to get this machine to do that. But how do we send in our intention? Okay, we can use a control this controller. Okay, so that you will get input from the human user and ex execute this output that we want. Okay, so this is power amplification, and it's something very common. On the other spectrum, or on the other extreme, we actually want the opposite. Okay, we want to make our motion more precise. Okay, sometimes our motion could be too powerful, but we want to do it at a more precise scale. Okay, so motion scaling is one of them. Okay, so one example, of course, is things like micro manipulation. In this case, this is a robot-assisted uh, minimally invasive surgery. So sometimes you want to get your robot into a very small place or space to execute some of the action. Okay, using direct hand, you might not be able to uh, execute the right precision. Okay, sometimes you move in a very coarse manner. You want fine. Okay, so the robot is actually good in doing that. But in this case, you have another um, console that allow you to execute the action that you want, but it will scale down to a more precise scale or dimension. Okay, so this is another example. And of course, part of this is also remote operation. So you don't have to be there to execute your intention. Okay, you want to do something, you can have the robot to do, but can be sent remotely. Okay? And ease of input is very similar to, of course, power amplification, but maybe in many different energy domains. Let's say if I want to control the temperature of this room, okay, you can, of course, um, burn the uh, burn fuels, okay, so that it will create a heat and then kind of lower the level of this burning to heat or just put in some coolant. Okay, but of course, if you do this manually, it's difficult, right? So if you have a control system, you can actually just by changing the knob of your air conditioning system, you can control temperature easy. Okay, so this is also ease of input. And compensation for disturbance is important because when we are dealing with environment which uh, is unpredictable, we don't know what are the external disturbance. Okay, so we need to design something that can actively cancel out the disturbance. Okay, so this is part of the reason for feedback control. Okay, so like the last part, we talk about uh, compensation for this disturbance. Okay, so that is actually the main reason why we want feedback control. Okay, so in a way, feedback control system is kind of used interchangeably as a closed loop control system. Okay, so what is the difference between open and closed loop, right? So remember previously we said that if we understand the plant uh, or we are able to perfectly model this plant, okay, we actually don't need feedback. Okay, the difference here, if you look at this control diagram, okay, it's quite straightforward. You know that when there's a feedback, okay, of what is happening in the actual state to the controller, this is actually feedback control. Okay, nothing complicated about this definition. Okay, feedback control basically means that you have, or closed loop control basically means that you are using this actual state and feedback to your control. Okay, so your open loop control system, okay, the controller out, or rather the control input is actually independent of the actual state. So it doesn't look at what is happening in, okay, in actual fact. It doesn't care. It just send in certain input to the plant. And hopefully this will what we want state. Okay. So it's like closing your eyes and you walk the number of steps. Okay. If you know that your target is 5 steps away from you, you close your eyes and you walk 5 steps and you hope that you'll reach your goal. Okay, that is open loop, right? But in closed loop, okay, your controller uh, actually is controller output, but we call this control input to the plant. Okay, your control input is actually a function of your actual state. It means you're actually looking at your actual state and coming out with something. So this control input, usually we use patient U. Patient U. Okay, this U is actually also based on your feedback. So of course, the control problem here is actually an optimization problem where we want, let's say our desired state is R, actual state is X. Okay, we want our X. Let's call this XD. Okay, so our desired state is XD, and the control problem is to um, make sure that X is as close to XD as possible. That means we are minimizing the error between our desired state and the actual state. Okay, so if we know our plant very well, we know what is happening here. Okay, we can design something, okay, where you will give the right mapping. Okay, let's call this U. Okay, to produce the right X. Okay, but in real life, do you think this is always possible? Do we always know this dynamical system very well? Okay? We may not have perfect knowledge, right? I mean, mathematically, if we want to define inertia for body, it could be very difficult. And to also model some of these uh, uh, components like friction, drag force, etc. Okay, so the dynamic itself, we may not have this perfect knowledge of the model. Okay, so that is of course one problem. Okay? And sometimes there are unpredictable external disturbance. Okay, so you would know. Okay, so if you are just closing your eyes and um, do 5 steps, you may or may not get to your target because the target might be more, or your steps might actually sit. Okay, because of the other dynamics of the system. So if you open your eye and see where you are going, okay, you can always feedback and control dynamically so that you know if your first step is too big, okay, the second step you take slightly smaller, and until the fourth step, okay, you decide on how big a step you want for your fifth step, okay? So that is a lot better, of course, if we look at this. Okay? So just to illustrate a little bit more, open loop for the same application, for example, if we want to heat up water, okay, if we have a beaker of water, want to heat up this water, okay, we can use this traveler heater, okay. This is actually a traveler heater because you can heater in, okay, and try to heat it up. Most of the time, if we want to boil the water, it's fine. We just send the right amount of heat because water boil at 100 degrees and then after that there will be latent heat taken up. So we don't actually need, if we want to boil water, we don't really need to measure the temperature. We know that it's going to reach 100 degrees as long as we send in the amount of heat. And then maybe sometimes we decide, okay, it's enough, we will take it out. So this is one example of heating out the water with open loop. So we can get to what we want, but maybe not as precise. Okay, we can only do 100 degrees. Maybe if we want the water to be 60 degrees or 70 degrees, not so easy. Okay, so of course, if we have closed loop system like a shower heater like this, okay, there's actually temperature sensor or thermal sensor kind of taking actual temperature of your water coming out of this shower head. Okay, so if you are bathing, you want your temperature to remain at the right comfortable temperature. Okay, so one way is to use sensor and feedback to your controller so that your controller can come out with the right amount of heat, okay, to change the state of your system. Okay, so that is of course closed loop. Okay, so this is very intuitive. Okay, in practice, this of course is not really there's no hard and fast rule on comparing this open loop and closed loop system. A lot of time it depends on the application, the condition, etc. But in general, in practice, we kind of see that if you are doing a closed loop, it's going to be more expensive most of the time. You need sensor, you need other computational resources. Okay, not as economical. But of course, like this this centrifugal governor, okay, is something very simple. It's also going to give a regulating effect, okay? So it depends. And design, of course, is a lot more complex in the also, but it can give you more accuracy, okay, because you are looking at what is happening. There's kind of like a ground truth if you find accuracy, okay, you have knowledge of the actual ground truth and so this is going to be more accurate and reliability. in a sense, if you consider a whole dynamic system, okay, because things are changing all the time, if you are just using open loop, of course, it's not going to guarantee a reliable outcome, right? So closed loop will be able to do that conceptually. Okay, so maybe yeah, just to make sure we are all on the same page. This class is ending at 5:30. Okay, you guys know, right? It's the same. All right. So yeah, let's maybe take an actual example, okay, to see if we understood this open loop and closed loop of the advantages of it. Okay, so imagine you are going to control the position of a mass, okay, whether it is on this end effector of this robot or on this translation stage here. Okay, so the stage uses both of them actually use stepper motor. Okay, I mean hypothetically. Okay, and so which mechanism A or B do you think will open loop control be more stable or suitable? Actually, not stable. Yeah. So when we say suitable, there's actually no right or wrong answer, but on your perspective. Right? So let's look at these two mechanisms. Okay. So who thinks that let's say for mechanism A, or rather for open loop uh, control, which one is more suitable, A or B? Who think is A? If you were to decide on using at least open loop for one of these, will you use it on A? Or who thinks that they will use it on B? Okay, most of you think that it's B, right? Which is, yeah, most of I guess is correct. Okay, of course, like what I say, it depends on your um, condition, application, and choice. But why do we say that B is actually better with open loop? Okay, that means you are just giving in command, okay, sending in inputs without having to read what is happening to M. Okay, but in this case, if you use, okay, let's say if you use open loop for this, okay, uh, and you try to use it for this manipulator out here, that means you don't, if you want to move this from one position to another, you send in certain input um, and hope that it will be there. Okay, the dynamic of this is actually much more complicated. Okay, it's actually not, you work out the dynamic equation, you will realize that the angle of all this, okay, there will be some sine and sine trigonometrical function. Okay, it's firstly not linear. Okay, secondly, you may not totally be able to work out the mass distribution of this link here. Okay, so for open loop, this is actually very challenging. Okay, but for this, uh, because the transmission ratio, okay, it's actually quite high. That means um, when you send a certain input, you move, let's say, for example, 360 degree. This is only about, let's say, 1 millimeter. Okay, so if you have an error of a few degree, it is actually not going to be very large. And you will need a very large force, okay, externally to disturb this thing. Okay, let's say if you try to move this by hand, okay, you push this, okay, you will need a very large force, or in fact, most of the time not able to do that. So any external influence is actually not significant to this mechanism, right? Because of the transmission ratio. But imagine for this, okay, let's say just a gravity or a little bit push here, okay, you try to leave this and turn the motor, it's actually very easy. Of course, some of the industrial robot is not easy because they have brakes or they have high gear ratio here, okay? But if this is just a direct drive, it's actually very easy for you to move this externally, okay? So anything external is very easy to influence our model. So it is not reliable if you try to do open loop. So of course, this is the explanation here, right? Due to the transmission ratio, right? Which is what we have discussed earlier on. So in the case of a manipulator arm like this, okay, you probably need to really have sensor to measure what is the angle. And if you have vision like camera to track the position, you will need that to feedback to your system. Yeah, usually I will give about 5 minutes of break uh, for this. But because today's lecture is actually quite simple, okay, maybe let's take a quick um, 3 minutes break, or we come back at 5, right? In case some of you need to go to the toilet. 这个签到的问题，for the attendance, if you have any problem, okay, just drop me a message on LinkedIn, okay? Okay, apparently there are two LinkedIn group for you to sign in. Okay, please sign in both because I'm also not sure which is the right one. But let's sign in both. I think the one that is uh, in the email sent to you should be the right one. Okay, so at this point of time, sign in for both first. We will sort it out with the Office of Student Affairs. Okay, so for this week, I think they won't be too strict. It's going to make sure that the system is working. Okay, so next time if there's any problem, just drop me a message in this link talks. Okay, yeah. So don't get too worried about this. I think for the first week, we'll try to explain to the office that yeah, there are some confusion. Okay, I think all is good. Okay, so just sign for both for these two lessons while we check and okay. Yeah, because yeah, also yeah, someone pointed out my mistake. I think the class should end at 5:20. Okay, but don't worry, today's is a very introductory lesson, so we will slightly speed up a little bit. Okay, 10 minutes because I forget that you guys need to travel uh, in between classes. Okay, so it should be ending at 5:20. Okay, I will try to keep to the time. But don't worry, the content today is more to get you warm up. Okay? Yeah, like I say, you can interrupt me if there's any problem along the way. Okay, don't feel shy. All right. Okay. So before we left for the break, right, we already looked at what is control system, some of the example, also explain why we need control system, in fact, feedback control system. Okay. And then let's take a closer look at the architecture. Not yet too in depth, but a very broad general overview of it. So remember this definition that we had earlier, right? This control system is designed to achieve desired output, okay, by generating the right input, okay, into a dynamic system. And most of the time, as an engineer, you need to specify certain performance criteria. Okay, so when you are designing a control system, of course, it should be within your design specification. So for the undergrads, okay, I'm sure some of you, even when you have taken signal processing and stuff like that, okay, you probably already know some of the criteria. In fact, in your lab one, lab zero, sorry, for the undergraduate student, if you are um, doing this lab zero, okay, you will actually be familiarized with MATLAB using one example of this transient response. Okay, you will plot out this transient response. What happened here is that, okay, let's say if I have a targeted outcome, let's say I want my output, okay, to be this value. Okay, so maybe this is my desired output. Okay, but as you know, the system is dynamically. So when we send certain input, it may not straight away get to the right position. Sometimes it will take some time to reach. Okay? Okay, sometimes it will take some time to reach and even go over the desired output. And then after a certain time, you will become a steady state uh, situation, okay, which is very much close to your desired output. Okay, depending on how you design your control system, okay, you can control how quickly it reach your target. Okay, you may be able to control the time it will take here. Okay, yeah. This is like there are a lot of terms that you will see in your lab zero, like rise time, okay, settling time, okay, when it will take to settle to a steady state value. And there are also things like overshoot. This is like overshoot. So let's say, depending on your application, your target, okay, or rather the design uh, goal, okay, sometimes you want to minimize the error. Okay, so of course you want to control this overshoot. You don't want it to, let's say if surgical robot, the most important thing is to make sure that you don't cut the wrong thing, right? So even though you can come back to the right position, once you cut, you can't reverse it. So you need to be able to design something that will have, in fact, no overshoot, okay? But maybe you can let it do slightly slower, okay? So you can uh, maybe allow a longer settling time or a short, sorry, a longer rise time, things like that. But later on, you will see some of these design criteria may be conflicting. Okay, sometimes you want to have this fast response. Okay, you may have a large overshoot and stuff like that. So that's why you need to understand how you can design this performance so that for the right application and choose the right parameters for your controller. All right. We will actually do this sometime in week 4, okay, when we do transient response and specification. Okay, but this is just part of the definition. Okay, why do we need to do this within a performance criteria? Okay, because as engineer, you want to be able to quantify uh, the right consideration, okay, to produce the right solution. Okay, so we see that this is feedback control. Okay, uh, initially, if naturally the plant will behave the way uh, it, it is inherent. Okay, but if you design a controller, you can send in the right input such that your actual state is very close to your desired state or perfectly, as far as possible, you want it to be ideally your desired state. Okay, and if you add a feedback loop here, okay, using a sensor to sense what is happening, you can actually design a controller that output something as a control input to your plant, okay, which will give you more reliable outcome. Okay, so the terminology that we are going to look at, okay, I think we touched on a few just now. Okay, plant is really the system, okay, being controlled. Okay, so it includes the whole dynamic system, a lot of time the environment as well. Okay, and sensor is this device that you use to measure this uh, quantity. Okay, is subjected to control. So actuator, okay, is actually the device that's acting on the plant. Okay, that's why it's actuator. Okay, so if it's a robot, it could be the motor, okay, on the joint, okay, electrical motors on the joint that will drive the motion of the link. So for example, in the case of the remote part. And controller is the part where you process this sensor signal and drive the actuator. So let's see this part. Okay, yeah, let's not complicate stuff. Okay, this sometimes this whole thing could be okay, designing right input to your system. So this is actually the control input, right? And control law is a rule for mapping our sensor signal to actuator signal. So in this controller, you will have some law that is governing what kind of signal that you should send in. Okay, after taking in the sensor signal, okay, you process this signal and come out with a signal that will tell your actuator what kind of input to send into the. Okay, so if you think of this as a electronic stuff that can take in signal and output signal, okay, to the actuator to uh, come out with the right control. Okay, so this is in a robotics context. In case this part here will kind of be like how this is really a signal, and feedback a lot of time is like sending in measurement signal. If you are looking at some textbook with the formal definition, okay, sometimes they will use notation like this, right? But don't worry too much, okay? Just understand the concept. Later on, this will be clearer to you as we on with example. Okay, so let's take a closer look at some of this actual situation. Okay, if we look at a system like this, okay, imagine we want to move our tool, okay, a micro tool, a very small tool. If you use hand to move, maybe it's not easy to control it precisely. Okay, you want to do some manipulation on itself, right? So this is difficult, but if you have a robot that can do very precise motion, okay, you need to come up with a control system that will control the robot to do this motion, right? So this is where your controller comes in. Okay, so in this case, we will have the architecture like what we have gone through earlier on, controller, actuator, the plant, sensor, etc. Okay, so if you look at this, you can map onto A, B, C, D, E, A, B, C, D, E, F, okay? They are actually correspondent to all these components in your uh, control diagram. Actually, the flow diagram, right? Your block diagram. Okay? So you can mentally try to see if you are able to map them looking at this example. Okay? So uh, let's say we are talking about the sensing system. So which part is actually a sensing system? A, B, C. Oh, okay, so what should our sensing system be? System? Something that take in information from the surrounding or from the front, right? That's correct. So it should be the camera that is taking, yeah, maybe some of you say that it's pixel coordinate is not too far, okay? In a way, is the pixel coordinate is actually the feedback. The camera is the sensor that's picking up this information, okay? Picking out this information and sending this feedback. So this pixel coordinate is actually the feedback from the sensor, right? So of course, this is one of it. And of course, the state, which is the output, is kind of like the motion of the chip, right? We are actually trying to do something that will control this motion of the chip. So this is actually the kind of like the output. And if we have a motion plan, okay, meaning this is where we want the actual, or this is actually our desired uh, output, okay, or the desired state. So this is actually a reference, right? Motion plan. We have a plan, we want to execute it. Our controller help us to take in this motion plan and then go into the actuation system. Okay, actuation system in this case will be the motors, right? Because the motor is acting on this plant or the mechanical system that will do the work for us. Okay, that will result in the right output. And so this mechanical system is actually our robot mechanism. Okay, so this is like an example to let you see how we can relate the, what we have learned, the conceptual uh, ideas in control system with actual example. Okay, did I get everything correct? That's good. Okay, so I'll first leave you to think of this more, but that's basically the terminology. All right. If we want to represent it in a systematic way, we can use a feedback control block diagram like this. Okay, so this is like a block diagram. So for those who did signal processing, it's kind of like you have this system, you have signal. Okay, so you send in something through this process, you will have output. Okay, so this was what we see earlier on. Now we have plant, and now we have controller here. This is the reference, and this is our output. Okay, yeah, because we don't put a sensor here, so we are assuming that our X and Y are kind of like the same thing. Okay, but strictly speaking, Y is measured output, something that you measure. Okay, so D here is disturbance. Okay, let's define. Okay, so if you work with block diagram, you probably know that uh, you can actually do multiplication. Okay, this E multiplied by C will give you U, right? So U is actually the product of C and E. Okay, for those who did signal processing, even if you haven't done this, it's actually not something scary. Yes. Yeah, so why will be the sensor uh, measure error? That's why we will send it to the controller to help us minimize this error. Oh yeah, yeah. So there will be some problem with your measured input because what you want is actually the state, right? So that's a very good question. Yeah, in later on you will actually learn how to do things like feed forward and stuff like that. Okay, they will actually be able to help you reduce some of this sensor error. Okay, yeah, that's a very good point. Okay, so for the architecture here is actually quite straightforward. So it's a simplified one where we just let y and x be the same thing. But in actual fact, x and y doesn't map correctly. In fact, later on when we next week when we do this state space modeling, okay, you will see that there is actually an output equation. Okay, your state space will actually have a state equation and output. That will actually answer your question a lot better. You will actually be modeling this sensor part as well. Okay, we will come to that later. Okay, so that's a good one, right? So basically, you will see this thing. The fundamental here is to multiply them. So whether it's a signal or a system, okay, it's just multiplication. So if you look at this, they are capital letter. Okay, if you still remember, why is it capital letter, small letter? There's a difference, right? Because it's in S domain. Okay, so actually it is in frequency domain. Okay, slowly you will remember this as we move on. So don't get too worried about this. Okay, so I will leave this for you to take a look. If you do this, all this relationship and you put them out, you will actually see that this feedback control can help us do two things. Okay, one is to make sure that we are able to produce a reference even when they are disturbance. Okay, you will actually be able to get rid of this disturbance, okay, with your controller C here. Okay, if you look at this equation, okay, of course, I will leave this for you to derive them. They are actually not too difficult, okay, but really your transfer function can be written as something like this, okay? So there are three terms, reference and a coefficient, disturbance and a coefficient, disturbance 2 and a coefficient. And in lab 4, okay, some of you will also further look at this, okay, in how you deal with disturbance. But if you look at this, what happens if my C get very large? If I use a very large gain for this transfer function, okay? You do a limits for this. C get very large, this part here should be 1, right? Good. So if this C for these two parts becomes very large, it will be 0, right? So what happened is that the effect of disturbance will actually be insignificant, okay? But your Y and your R will be as close as possible, all right? So this is, of course, what we call reference tracking or reference tracing, okay? To make sure that your output and your reference is about the same, and to make sure that your disturbance is as insignificant as possible. So this is what we call disturbance rejection, okay? And this is reference tracking. So having a closed loop system will help you do that two things. You can take away this, or you can compensate for your disturbance, reject your disturbance, and you can track your value, okay? So that is very much about the end of this, okay? Yeah, I'm supposed to go through a very quick, maybe just 3 minutes to very quickly give you a perception of this for completeness, okay? Basically, even in the very early days, we are able to already come up with control system like controlling the water level or pressure like this. Sometimes they use this to measure the time. Okay, of course, you can work out something very precisely to measure the time, but you need a control system to be able to control the height of the water. And you know that the flow of the water will depend on the pressure, which is also a function of height. So this become not as simple as it looks like. So you kind of need two different a coupled tank system like this. And so in the past, they actually have something like this. Of course, you can have sundial to look at the time, but if you don't have the sun, then you can't really tell it. And so having something like this incrementally tell you the time is also useful and govern this governor, centrifugal governor we talked about earlier, is one of the representative control system sort of like invention during the Industrial Revolution. Okay, and eventually we have more sophisticated stuff, and we have good electronics technology. Okay, control system become more and more powerful, and in future, of course, we will be seeing more digital stuff that can come in to help us design a sophisticated control system. Okay, so of course, I will leave this for you to slowly think about it. Okay, but next lecture we will look at things like state space model. Okay, we will try to model the dynamic of the system using state space model, where you have your output equation as well. Okay, input your state equation and output equation. All right, and also linearization. All right, so I will see you on Thursday, and we will be doing these two topics. Okay, thank you so much.